The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, moving on with the session here, I'd like to introduce Mike Russillo, and again, we're trying to do our best here to make this a generic presentation. Inevitably, we mention a name or a proprietary name, but the intention is to provide a generic presentation about the concept of voided slabs. Mike is with one of the suppliers, and he's going to talk about a project that's very exciting it's under construction, very close to completion in the U.S. So please join me and welcome Mike Russillo.
Thank you, Mike. I'm Michael Russillo. Okay, and I'm going to present about the Miami, just a little better, Miami Art Museum, which is under construction. It's going to be finished shortly, and we'll get into some of the particulars. I'll just give a very brief description. We all sort of know what voided slab is, but I'll tell you from my perspective how I look at it. We'll talk about the concept and how we implement this concept, run through a lot of construction photos of the particular Miami project, and it also had some special features which you just can't avoid them. They have nothing to do really with the voids, but they're great for an audience that's interested in concrete construction and really some of the beautiful things that can be done, and certainly give some facts about the concrete and the project itself. At the end, we'll have some time for questions, of course. The Miami Art Museum, which I keep calling it, is now going to be called, when it opens, the Perez Art Museum Miami, and I guess if you have a couple of $1 million, you can get a museum named after you, which Senor Perez did, which is great. It will open this fall. It's on target, I think October, November, and aside from the numbers of about 80,000 square feet of interior space, but you can see a lot of the exterior space has concrete on it. But on the interior space, there was some 120,000 square feet of interior space, and we used voids on about 80,000 square feet of it. And why did they use it? Why did they use the voids to begin with? They had a lot of large spans for different room sizes that the architect wanted, that the program required. The architect really wanted a flat slab. He did not want to see beams in the normal sense, so he fell in love with a flat soffit. He also fell in love with the fact that he wanted recesses. They called them rebates, but they're recesses that occurred regularly, 2'6" on center, that would recess the light fixtures and the sprinkler system. So those were a couple of the things that drove him to want concrete and want a flat slab. He also had a lot of cover required because it's right on the water, and he needed to reduce the weight. In this part of the world, in Miami, everything was on piles. So they're also looking for this LEED certification, which I believe they'll get. So to the basic idea is, let's take a lesson from Mother Nature. We learn a lot from Mother Nature. The bone, if you look at the bone of a bird, the wing has to take a lot of stress, and it does it in a lightweight fashion by having a lot of void, probably more void than structure. But in our case, we're eliminating that concrete in areas, as Mike put it, where we really don't need it. It's not doing a lot of work, and we're leaving it where we are. We've implemented that idea with Kobiaks and the other systems by having voids made from recycled plastic. Keeping with that green tradition, we have to have recycled plastic, and we position those in the zones where they do not, where they eliminate the weight but don't eliminate the structural capacity and the strength. And we get, what we like to remember is we're going to be able to get a biaxial transfer. So this is what the framing would look like. It would be formed just as you would form a normal flat plate. Whatever you would use, whatever is common in that area, this is what they would form, a normal flat plate. Then a bottom mat of reinforcing steel would go down, just typical. The voids come in cages in the system that I represent. The voids come in a cage. Cages are 8 foot long by 1 void wide. They would sit on the bottom steel, perpendicular to the top layer of the bottom steel. They would just sit on it, be spaced appropriately, and then those cages become the supports for the top steel in the area where the voids are used. In section, this is what you would see: the formwork, the bottom mat of steel, the cages containing the voids, the top mat of steel, and when poured, as Mike pointed out, the staging, and this is, I mean, we've done only a couple of jobs here in the United States, but literally hundreds of jobs in Europe. They start in one corner and pour the concrete, and by the time they get back to that corner, it has had its initial set. And the first lift or first stage of concrete engages the bottom mat of steel and the bottom wires of the cage. And once that's done, when you come back, it doesn't have to be hard, it just needs to be semi-set up. The top stage is poured. One of the first things done, of course, is to take the structural drawings, which would indicate the areas that the structural engineer wants the voids, and has used that displacement, that weight reduction into his calculations for columns and foundations. But this is one of the plan of one slab of the Miami project, and you see, probably can't see it too well, but you see all the different void sizes. We had 6 different sizes of voids on this project because we had 10-inch slabs and 24-inch slabs and everything in between. And then you'll see some of the sections. The rebates are shown. Some places had rebates, some places did not, and we also had areas where we could indicate, and you'll see a little better as we get further along in the slides, how the reinforcing steel was put in those. But it's a little better blow-up, if you will, just to give you an idea of the different types of voids and in the different sections. So it was flexible in that it could accommodate various spans and various conditions. This just shows 3. First thing that would happen, and we'll get into some of the on-site photos now that show you really what happens on the job. In our case, the voids come delivered in a truck in bundles. The bundles, as you can see there, are stacked somewhere on site. A little better close-up of the cages. These are the largest voids. They're 450 millimeters. And these cages are held together in bundles, and the bundles are held together with just rebar, number 4 bar, that after they get up on the deck, they take that number 4 bar and they'll use that around their openings as miscellaneous steel. So there's no waste of material, of packing material. They're just picked up with a crane. They're fairly light, so it's just a matter of how much you can grab and throw up on the deck. Again, beautiful Biscayne Bay in the background. They're set up on the deck, ready to be put into the slab, the next slab that they're going to do. The placer, actually the fellow who installed all the reinforcing and the rebar and all the voids on this, when he saw this particular photo, he said he should have fired this fellow. He's only carrying 1. You should be carrying 4 or 5 of these. They're very light. I pick up 2 or 3 of them, but they were 8 foot in length, but mostly air, as it was pointed out. They're laid down on that bottom mat, and they're spaced. We use a template, a wooden template with notches in it to keep the spacing right, and they're tied to the bottom mat, say 3-4 ties per cage. These are some of the, I'll go back a second. These are what we call our slim line. These would go in slabs from 8 to 14 or 16 inches. We would use these ellipsoid shaped voids. When the slabs get thicker, then we go to what we call an econoline, which is a spherical shaped void. And again, we're using a template to lay these out, keep them straight and lined up. These are the 450s in place. You can see they're really large, major displacement of concrete. These slabs probably, with the rebates, they might have been 26-inch slabs because they lost so much of the depth with the recesses. And you do get some interesting views on site, as you'll see in mine and Dan's photos. There's some interesting things that you're not used to seeing. Here they are. Also in the background you can see some of the upturn beams. We'll talk about those a little bit. This project had a lot of different features. There you go, the upturn beam. And here you see areas with could handle and accommodate a lot of congestion, a lot of conduits being put into the slab, top steel starting to go down. Here you have the top steel sitting on those cages, getting ready for the pour. Another view showing the same type of condition. Now, all of these slabs are going to be exposed, or most of them are going to be exposed, so a great deal of care was taken in a lot of areas, in the formwork and in the clean out. So they wanted to clean it out very carefully so that they wouldn't have problems later on and have to spend time later on. So they blew out between it. What made it a little more difficult on this project, again, with these continuous recesses, they had to blow everything in one direction and get it off the deck, but as you'll see later on, I think all their efforts really paid off. All the concrete was poured. Really nothing super special about the concrete. The concrete itself was good quality concrete, and what they do in Florida to keep the shrinkage down, they did, but it's nothing extraordinary. The first stage is, as you see here, poured, ready for the second stage to come on it. The top steel's all down, of course, as part of it. There's another view showing a larger deck. In most cases, in Europe, as I said, and also in a few cases here in Miami, this was all done in one day, but in Miami, they did a number of these where they waited 2 or 3 days between the pours because they had a lot of other work to do, this upturn beams and things. Digress just a little bit from the voids because some of the special features of this building really should be of interest to you. They did a mock-up just to try to address ahead of time some of the special features that you'll see. They had these rebates that you're seeing here, 4 inches deep, 2'6" on center. They had an exposed ceiling. They wanted it to look good. It's going to be an art museum and it's going to be wide open. And they had textured walls. They weren't just textured walls with formwork. They needed to look naturally textured. This is a little close-up on that view, but this was all done with a chipping gun by hand. All this texturing was done and there were different textures, but this was one that they did. Give you just an idea of the magnitude of this work, of these fellas here were chipping away on these walls. It was amazing. Some of the views that obviously from the outside, the photos from the inside, I wasn't able to get too many of or any of, but this is some of the end result. A lot of these are exposed ceilings with the rebates, with the textured wall, and if you'll notice, an amazing cantilever. If you picture those rebates, those are 2'6" on center, so that cantilever is really hanging out there, and it's only able to do it because the wall above it acts as a big deep cantilevered beam. Okay, they had a lot of shoring in a lot of places that they left in until that segment of the building was complete. They left it in the whole time because of the way this is constructed. It's really a bunch of boxes, offset boxes, where the walls become the support for the floor below it, so that you end up with some really large spans and some really unique structures sitting up on a few columns. They're sitting up some very large areas. And they use different textures. Some places they're going to leave these walls smooth, some places they're going to brush them, some places they're going to hand chip them away. The rebates, these recesses that were put into the slab, had to be done very accurately. They're going to read them. You're going to read them very clearly, so they were very careful in laying them out. And of course, the gymnastics involved for the structural, for the reinforcing steel, had to come over these. A little close-up will show you how this is. Now, this is all bottom steel you're seeing here. I got this photo to show how that laid on it. The reinforcing steel had to be fabricated to go, over the rebates, the bottom steel in one direction. And in this particular case, on this particular job, they weren't able to take advantage of this biaxial forces. The rebates themselves caused it to be more of a one-way slab, but this is how it was accommodated with the reinforcing. And they wanted a 2-inch cover on all the slabs because of the proximity to the Biscayne bed. From underneath, they left the shores back in, showing those rebates. And this was still under construction, hadn't even been cleaned up yet, but these slabs really look good. When you saw them, it was impressive. The final result, the vision of this architect, you could see was going to work. Here you see some of the exposed slab from the underneath, the ceiling, as well as the wall going up, all roughened by hand. Again, a lot of special conditions. Mike and I had the fortune of walking the job with the structural engineer who designed it, and every corner we turned was a special condition. Here they used the structural steel beam, wrapped, of course, getting ready to be placed, to be part of the structure where they found they needed a structural steel beam in this case. In other cases, they used upturn beams. Again, they wanted nothing to be dropping below the ceiling. And when you do all that, you have some special formwork. I mean, this is a hanging formwork to accommodate some of the conditions that were required on this site. So it was a lot of special concrete work and formwork. They had a hanging beam. They used the Dewey-Dag bars to hang a beam from above. They had slope slabs because they were going to have an auditorium. So, some of this is not that unusual. You'll see in the right-hand corner there a stack of voids ready to go in. They also had a lot of exposed beams, and you can see they're so close on center. They're certainly not structurally required to have this many beams, but again, it was an architectural determination that in this area they wanted to have these beams, so quite a few of them, and shoring that goes from them up. They supported underneath while they were doing loading during construction. But the end result of it really looks good. I mean, what was done, or all the efforts that were done, seemed to pay off very, very well. Again, all these walls, lots and lots of walls. So they prefabricated a lot of the walls so that they could fly them in. And they were extensive, and they were done very carefully, and they were inspected very carefully. And the placing of the concrete in them was done carefully. But all those efforts really came out to some really high-quality finishes on those walls. The formwork that was used was done, minimize any kinds of deflections and to keep the surfaces nice and smooth. I'll run through some construction sequences to kind of show you how this goes together. Again, it's all on auger piles, so the loads go down into not the best soil in the world, but starting off, they saw all those beams going in around and the first elevated floor going in. And then you start seeing these boxes coming up, these walls with to outline these boxes of different shapes for the different room sizes and different displays that would go into different rooms. Then the slab would go on. If you notice, the slabs overhang significantly. Obviously, they're not there by themselves. They're going to be shored until the next series of walls go up that actually end up supporting the floor that was previously poured. So the walls above are supporting the floor. Then more walls are going up, and these don't line up with the ones below, but now they support part of that floor. And then another slab going on there. and then some beams up on the top because they wanted to have a hanging garden effect, if you will, and they put all those up. In section, this kind of shows you how the walls are there and the upturn beams are there and everything is there. Then also they put a plenum in because they're going to put all the AC coming in from the floor and going up onto the plenum space that's provided for the final. I have some aerial photos that actually also show this construction and the structural gymnastics that the engineer had to do to accommodate it. This is obviously up into the second level, and you can see some slabs here that are poured, some are getting ready to go. The next one shows some more of the walls up, again some more slabs being placed, some voids in place, some voids stacked up ready to go. Down in the lower left-hand corner you can see the storage area where we kept the voids, kept them all available. As we get further up, actually there looks like a bundle of voids being delivered sort of in the middle left. I don't know if you can see that, hopefully. And just about most of the concrete work here is just about done by now. A little close up on how some of those upturned beams look. So lots and lots and lots of concrete. And the end result is some very interesting geometry and very interesting architecture that's going to take place. This would be the entrance as you approach it, obviously, with a lot of the shores. And I was speaking with the structural engineer, and even taking the shores down had to be done very, very carefully. They had to think of which ones they would take down first and second, and which ones they would leave in. So some of the numbers involved. It's a good-sized project. Like I said, we had about 120,000 square feet of interior space, and we covered about 80,000 of it. Good-sized rebar job, 3,000 tons. But we had 6 different sizes to accommodate the different slab thicknesses. But really probably one of the big impressive things here was the amount of weight that was taken out of the structure, which was a heavy structure to begin with, but that much weight taken out resulted in making the foundation more economical. Again, some of the interesting things that were done, and this is only just a small piece of them, that were done to make it such a quality job. That part of the world doesn't have the best reputation for the best concrete work, but this concrete work was excellent. And it's a tribute to the concrete contractor, the architect, the engineer, everybody. They did a lot of things using special plywood, using special finish work to keep the finishes smooth, using backup on the wall forms to minimize deflections. Of course, they had a lot of cover, 2-inch cover. They had the rebates. This all added to the thickness of the slabs. But they used, from what I understand, they only specified 5,000, but basically ended up with 6,000 psi concrete. It had some admixtures in there to minimize the shrinkage. So I think a project like this, certainly the credits are I wouldn't want to do anything without giving credit. The architect, his vision is really something to behold when you see it up front. It's beautiful. This Herzog, I guess, was the main design architect on it, and the structural engineer my hat goes off to for accommodating and being able to satisfy or meet the challenges that were created. The CM, of course, Baker Concrete, we all know, joint ventured with a local concrete contractor, and the reinforcing was installed. So this is what the project will look like. It's in its final picture looking from Biscayne Bay, and it will open in the fall, and it will house some works of art, I'm told, that have not been made public. But the building itself, that's really a work of art for us. And for the structural side of it, for the structural engineering aspect of it, this was a structural engineer made a great opportunity using concrete, using cast-in-place concrete in this place, to really make a beautiful structure. So this is my presentation, and if we have any questions on that, we'll entertain them.
Yeah, I would just like to add a comment that when I walked the site with Mike Rustillo and the structural engineer, what the structural engineer from Arab relayed to us is that they have looked at many schemes, and this is actually born as a structural steel project that was then converted to concrete because of the voided slabs. The reduction in the weight, you saw a cross section of the Galleria that shows some open spans up as much as 90 feet, I believe.
Oh, yeah.
And this reduction in the weight is what made that possible. And then the combination of the structural scheme with the boxes, worked in with the upturn beams, supporting slabs, allowed them to have these cantilevers and really give the architectural feel that the architect was looking for. So this was really exciting. You didn't talk about stiffness modification, but so if you're looking at, so go ahead, Mike.
Okay, well,
if you compare, I guess, a slab of the same thickness and then...
The same slab thickness, if it's a 10-inch or 12-inch, whatever the stiffness is, it's about 92%, between 90 and 92% for the voided slab. So that needs to be taken into account when you do the finite element program, and it's just one of several ways in various programs. However, you've lost so much weight, you've taken so much weight out of the mid-span area that it more than accommodates it in terms of deflection. So you really end up with a lot less deflection on the same slab. You could actually do the same span with a thinner slab if you so chose, voided, because of the weight if deflection were controlling. But if you, for some reason, want to look at a 10-inch slab, put the voids in, yes, you'll have a modification of a 90%, 90 or 92% on the stiffness, but the weight will be so much less that the deflections will be significantly less, and deflection ends up being not an issue. And we've done it with post-tensioning in Europe and without, which is a whole nother ballgame, but it's certainly doable with both.
Yeah, and actually, when you go to longer spans, the system is even thicker, so you're actually picking up stiffness. So if anything, the system becomes even more efficient. And from vibration standpoint, you're gaining stiffness, you may be reducing some mass, but I think the two are balancing each other. And we're actually next present. So any questions for Mike before I jump to the next? Yes.
Yeah.
Would you mind coming to the microphone, please?
Why do you need to pour in two phases?
Well, you need to pour in two phases if you don't have another way of holding down the voids. You could come up with a way to hold down the void, but if you don't hold the void down, it displaces. Just like you learn from Mother Nature, you can't fool it. It's going to displace anywhere from 30 pounds a square foot to 90 pounds a square foot, depending on the void. So you would pour in two stages unless you came up with a strap down. There's an idea of the plastic recycled void.
Yeah, so if you pour above the equator of the system, if you will, then you're going to want the system is going to want to displace. And you've got so many voids that there's not enough mass on the reinforcement from the top mat to hold it down and keep it in place. So the only way to do this, and by the way, we talked to the contractor on site that placed the concrete. There was no issue. In this particular case, it was kind of an unusual circumstance where time is not so much of the essence, but I think we'll, in other projects, it's fairly quick to go around and, curing 3 hours, perhaps, 3.
Not even. After an hour and a half or two, that initial concrete has its initial set. It's just enough to hold it, and then now you're pouring the full slab. So if it's a 12-inch slab, you've poured 3 inches of concrete for 10,000 square feet. By the time you come back, you start filling it all the way up. Now I have another contractor, and he's going to hold it down. He's going to hold that bottom mat down. He thinks that's simpler, just drilling through the formwork. Yeah, he's not an exposed issue. He's going to hold it down. But otherwise, you would do it in two.
And in the case, the workers stopped 3 days. I heard.
Well, in that particular job, there's a big area, so they weren't stopped. They were working in other areas, but they had these upturn beams that required additional formwork. And in forming an upturn beam, you actually have to hang the form. They tried to show that it's kind of crazy formwork. So they would pour an area and come back and finished that particular section of the slab 3 days later.
And do you have shear connectors for
Well,
bonding?
the bond is the two issues. One is you have a very, very textured slab that you're connecting to, and I think Attila addressed that in one hand. Also, the wires that connect the voids, the wire cage, has, and we give that out, has sufficient structural capacity to help that transfer.
So this is a sample of a cage for another system, but even though they are not counted towards the structural calculation of the shear capacity, it's there anyway to bridge the cold joint. And this is very similar, as you'll see in a little bit, with the casting place concept, where you have a precast panel that works with compositely with a casting place. Yes, I'm sorry.
Yeah, I have one more
Oh,
question.
Sure.
Your slide, I saw some beams, inverted beams.
Yeah, upturn
Can
beams.
you use these slides on columns directly?
Can you? Oh, yeah, that's what it's normally done. It's normally done in a flat plate. This was,
But you have to make it solid, just like a waffle slab.
Okay.
Yeah.
yeah, the area around the column should be kept solid, so that's the area where you have solid concrete and roll. Yeah, you'll see it. The normal case, again, this was Miami was a special job with other.
Those balls, they don't explode with vibrating?
No, they don't explode. They don't explode.
You can hold one. I mean, this is a pretty slippery. So.
Yeah, they're pretty hard. We had some other
Yeah,
questions?
no question. Would you mind coming to the microphone? Only because this is being recorded for the website.
Other than the architectural implication of the ceiling as exposed architectural concrete, what's the major structural difference between this system and a conventional two-way waffle?
Well, the only difference is it's a waffle with a soffit.
That's it.
It really is well, that's one of the ways I explain it to people. Everybody's done waffles, but it's a waffle with a soffit. In some ways, it's a little, I think, a little more flexible than a waffle with a soffit because the bottom steel can be at any spacing you require. It doesn't have to be in the ribs.
And you get a continuous diaphragm.
And you get a two-way biaxial, and that's the way it performs when tested. You know, we've tested this. It performs, it deflects. It's just like a two-way flat slab. It's just a lighter two-way flat slab.
Is it faster in terms of forming? Because you're not building pans?
The form, in terms of, instead of waffles,
Right.
I think it's much faster, and you're not taking pans down and cleaning them and putting them in. You're just forming a flat plate, done. You know, it's just a forming of a very, I mean, from the forming perspective, it's a flat plate. From the installation perspective, yes, there is a one element. You have to install the voids, but those voids replace the tall chairs you would put in to support the top steel. So you get a little bit of a trade off on the labor aspect. Didn't appear that it slowed down the pours. If it was going to take a fellow a day to put 2 days to put that steel in, it didn't take him any longer.
What I want you to walk away from this session today is that we're looking at yet another solution in concrete for long span buildings, okay? And so this is really the consideration that I'd like you to walk away with. It's another solution. When it comes to the pans, there is a cost associated with renting pans that it's probably more than this. So something to consider with that. We have a fellow here from McHugh that has looked at the two systems. I don't know if you want to add a couple of words just to instigate a little bit of discussion here.
Hi there, Ian Conley with McHugh Construction in Chicago. And yes, I've spoken to all the gentlemen up here on the stage about various projects trying to find a void slab, but in particular with regards to waffle slabs, the voids are significantly more cost effective than actually buying or renting the waffle voids and then actually recycling them and whatnot. So it is by far a more cost efficient method.
Okay, thanks. You have a question?
No, I just simply wanted to add your question regarding the difference between the waffle system structural perspective, constructability perspective. With the waffle system, you have a set of rectilinear beams. So basically, you are running your analysis sort of on a set of beams that are running perpendicular. In case of the waffle system, you have these nice round bubbles, which basically allows the stresses to flow around the the system. That means that you are putting your system together in a way that they are working in tandem in two directions much better than the bottle system. So it adds by nature a little bit better capacity as such. That's all. And analysis-wise, it obviously should be different slightly.
Okay, we're going to move on to the next speaker, and then we'll have some more time at the end for more questions. Mike Russillo, thank you very much for your presentation.